Assalamu alaikum dear students. Today we are going to discuss hydrometer analysis. This is the second part of grain size analysis or mechanical analysis lecture which we discussed last time. So let's begin. As we discussed earlier that soil rarely consists entirely of a single size grains. Usually there are different particle sizes in soil, and to classify the soil and to properly know the properties and the behavior of a particular soil, we need to know how much percentage of a particular size particle is present in a given soil sample. To achieve this purpose, we do the grain size analysis, which is also known as mechanical analysis in some of the books as well, which is basically the process of determinations the size range of the particles and their percentage by dry total weight in a given soil sample. The mechanical analysis provides us with sizes of particles present in a given soil sample with percentage of each size, and for that purpose we use sieve analysis for coarse grain soils, and for fine grain soils less than 75 micron we will be doing hydrometer analysis. So for distinction purpose over here, we said that all the particles given that has a size greater than 75 micron or 0.075 millimeter will be considered as coarse grain soils, and if the soil particle size is less than 75 micron or 0.075 millimeter, then this soil will be known as a fine grained soil. So for this, in the previous lecture we discussed about sieve analysis, which was undertaken for the particle sizes larger than 75 micron or 0.075 millimeter. 75 micron is equal to 0.075 millimeter. So those particles were measured, their percentages and their sizes were measured using various sieves of larger opening, and then the preceding sieves were used with a smaller opening size in the bottom. They were shaked, and the soil particles which passes through sieve number 200, which has a size of 0.075 millimeter, they were collected in pan. So those soils will be then further analyzed using sedimentation analysis, for which the hydrometer analysis technique is used. There is another technique which is known as pipette method as well, but we will be discussing hydrometer analysis technique today, in which we have the equipment include graduated cylinder. With that we have got a rubber top cap as well. We have hydrometer, which you can see over here. We have sodium hexametaphosphate solution, which is used as a dispersing agent, which we will discuss in a while, and then for mixing of the soil sample and the dispersive agent we use the mixer as well. So all the equipment is available in your laboratory, and once you are conducting this experiment in the laboratory, then you will use all these equipment to determine the hydrometer analysis and particle sizes of the soil, which is finer than 0.075 millimeter in diameter once you are in the lab. So here we will discuss the theoretical portion of this hydrometer analysis. So hydrometer analysis is basically based on sedimentation of soil grains in water. So what is basically process of sedimentation? In this we mix the soil sample. We usually take 50 gram, in some cases for the larger cylinder up to 100 gram samples is taken as well, but in your case in the laboratory you will be taking 50 gram of soil, and we put it in a graduated cylinder along with 1000 ml of water. So this is a graduated cylinder with 1000 ml or 1 liter volume. In this we basically mix the soil with the dispersive agent, and then we place the soil solution in this graduated cylinder. Now what will happen in this case is that you know that according to Stokes law, which we'll discuss in a while, the larger particles, they will settle quickly compared to the smaller particles. The smaller particle will remain suspended for longer amount of time compared to larger particles. So in this way, initially you will have such kind of distribution of particles in the soil sample, in this solution. So after passage of time, what will happen is that the larger particles will quickly settle and the smaller will be still settling. So at any time, the specific gravity, initially the specific gravity of the solution is uniform. Over here you can see the specific gravity of the top portion is different, the middle portion is different, and the bottom is different. There will be more specific gravity at the bottom, there will be intermediate specific gravity over here, and there will be less specific gravity in this location of a solution. So what we use hydrometer for? We use hydrometer to measure this specific gravity. So if the specific gravity of the solution is more, it means it is denser solution, it has got larger particles in it beside water. But with the passage of time, the specific gravity will reduce, which will indicate that there was a larger particles in this solution which have settled down to the bottom, and that this basically indicate. So if the soil, particular soil, has a more larger size particles, then its specific gravity will quickly reduce, because the larger size particles, if they are more in the sample, they will settle quickly. But if the smaller sized particles are more in a given soil sample, then the specific gravity of this sample after given time t, it will have less reduction. So it means that the particles have not settled, they are still in the motion, in the process of settling. So for this purpose, we use this hydrometer, which is a simple glass tube, which you can see over here. There are graduations in these portions which are known as hydrometer reading, and then you have the bulb portion over here. In the bottom there is a mercury or some heavy weight which is known as ballast, which keeps it vertical in the solution, which you can see over here, and it measures the specific gravity at the center of this bulb. Okay, so once if the specific gravity of the solution is more, if there are more bigger particles in that, the hydrometer will dip to the lower depth. Okay, and the hydrometer reading will be less. But if the specific gravity of solution is less, the hydrometer will emerge to a greater depth in this soil, in this solution, and the hydrometer reading will be more, which will be taken from this point. Okay, so this is the process which you will be doing in the laboratory to perform this test. So moving on, we will basically discuss what is the theoretical side of this hydrometer analysis and how you will determine the particle size distribution of fine grained soil. So as we discussed, we will place the soil with some dispersing agent in the water and then allow it to settle. So why we mix the soil with dispersive agent? That is because the clay particles, they are very small in size, and 2 or 3 particles can stick together and make a bigger particle and settle quickly. So what you need to do, you need to mix dispersive agent. The function of dispersive agent is basically to disperse the soil, to separate the soil particles from each other. So if 2 or 3 particles are combined, they are sticking to each other, they are making a bigger particle. But if you separate them, actually their particle size will be small. So if they combine together, they can make a particle 3 times size of their own, which is not actually true, because they are combined together and then they may be separated as well. So that's why we will use dispersive agent while mixing the soil with water to make sure that all the particles are separated from each other. So once they are separated from each other and they are mixed in the soil, they will travel downward. When you, if any particles which is heavier, we know the soil particles are heavier than the water. We already discussed in the specific gravity of soil solids, and we said the specific gravity of soil solids ranges between 2.6 to 2.8, so it means they are 2.6 times to 2.8 times heavier than water. So if you put a soil particles in water, they will settle to the bottom eventually. Okay, sometimes when you mix some clay soil with water in a container and you come back next morning and you see that the clay is settled to the bottom of the tank, and in the top you've got water which does not have any clay in it, and it's purely clear. So that is because of this sedimentation. The soil particles have settled over this period of time. So what will happen when you place these soil particles in soil? They will settle down. Okay. Now their downward movement will depend on their shape, whether it is spherical, okay, or any other shape. Now usually I've considered spherical shape over here, and we will assume it to be spherical, but actually the soil particles, especially clay particles, which is the purpose of determination of hydrometer analysis, they are flaky or sometimes needle shaped. Alright, so that's why it will depend on shape. If it is spherical shape, it will settle quickly. If it is flaky shape, flake is like cornflakes. Okay, I showed you some scanning electron microscope images of the clay in the introductory lecture, so if you remember from there. So they are sometimes flaky, sometimes needle shape. Okay, so it will depend on shape. If this shape is there, then it will settle quickly compared to these shapes. Then it depends on size. If the size of the particle is more, it will settle quickly, of course, and if the size of the particle is less, then it will settle slowly, but it is also related to the weight as well. So if the weight is less, size is more, then sometimes it works the other way as well, because if something has a larger size, then it will have greater viscous drag force on it, which we will discuss in the next, which is viscosity of water. Viscosity of water usually constant. We perform the test at 25 degrees centigrade, and we consider the viscosity of the water constant at that temperature. But why the viscosity is important? Because when the soil particles will be settling downward, there will be viscous drag force acting on upward direction, and also there will be force of buoyancy as well, but that we will consider constant over here. So viscous drag will be preventing this particle from moving downward. Alright, so when you place the soil particle in water, initially it will be settling down quickly, and the viscous drag force will be increasing on that till the time it reaches a terminal velocity where its downward motion velocity will become constant, and at this time the viscous drag force on this soil particles will be equal to 6 pi eta RV according to the Stokes law. So this is the upward drag force on the soil particles. This will be acting in downward direction, and gravity will be acting in the downward direction, and viscous drag force will be acting in the upward direction. So this force diagram we will be using for calculation of our settling velocity, and from that we will be determining the particle size. So according to Stokes law, if you have this situation, then your settling velocity V will be equal to density of soil solids minus density of water divided by 18 eta into d square. Okay, this is simply determined from equilibrium of forces over here, of the gravitational forces and upward drag forces being measured over here. Pi, its value is 3.14. Eta is the viscosity of the water, which is usually considered constant at 25 degrees centigrade. I will show you the value later on. R is the radius of this soil particles, which is equal to diameter divided by 2. So you can write d by 2 in this equation as well, or sometimes r as well. And v is the terminal velocity, which you can see over here. So if you calculate the force equilibrium over here and rearrange the equation, you will arrive at this equation, which is generally known as Stokes law, which is the settling velocity is equal to the density of soil solid, the density of the particle, minus density of water divided by 18 into viscosity into d square, while d is the diameter of the soil particle. So from this equation we can determine then later the value of d. So as we know from Stokes law, V, or the settling velocity, is equal to the density of soil solids minus density of water divided by 18 into viscosity into d square. Now we want to determine the particle size d, so we will take this density and viscosity to the other side of the equation. Okay, so we will take this quantity to the other side of the equation, and because this is d square, so the other side will be placed in the square root as well if we are to write d. Okay, so we are taking the square root of both sides. So now you know that velocity v is equal to distance divided by time, or length divided by time, or length traveled by something in a given time period. Okay, so let's replace velocity with length divided by time, which is the length traveled by this hydrometer in a given time t. So immersion length, initially it was immersed to this point, and then after time t it will be immersed in up to this time, because when you place it in water, initially it will show you the reading somewhere over here, but as the specific gravity of the solution will be reducing, it will be going inside the water. When you are performing the experiment, you will observe this. So that's why I am trying to write it in terms of the hydrometer reading, or L over here, divided by the time. So we also know that we want to eliminate the specific gravity of soil solids over here from this equation. So let's replace this, and from our previous lecture, you know that specific gravity of soil solid is equal to density of soil solids is equal to specific gravity of soil solids into specific gravity of water, simply from the definition of specific gravity, because we know the specific gravity of soil solids is equal to the density of soil solids divided by the unit weight of water, or density of water. So density of solids divided by density of water, density of anything divided by water will be specific gravity of that thing. So shifting this density of water to this hand side of the equation, so density of soil solids is equal to specific gravity of soil solids minus unit weight of water. So replacing this into this equation, and then taking rho w common from this. Okay, so this will be gs rho w minus rho w. So rho w and rho w will be common, so take rho w common from this, and you will have gs minus 1 into rho w. So this is the equation which you got to determine the size of the particles within the soil which are settling over here according to the Stokes law. So if we know the quantities on the right, we can determine the size of this particle. So now writing or converting them into some measurable units which we will be using. So let's say if we are using viscosity in gram second per centimeter square, density in gram per centimeter cube, and length in centimeter, and time in minutes, and d diameter of the particle in millimeter. So by placing these units over here and solving this further, so you will see over here, because these are in centimeters and we want to take diameter in millimeter. So 1 centimeter has 10 millimeters, so we will divide it by 10. Okay, because on the left we want to have diameter in millimeter, and on the right we want to provide everything in centimeters, because the immersion length or the reading on the cylinder, they will be all in centimeters. So on right hand side you have got centimeters, on the left you got millimeters. So that's why I am dividing this by 10, because 1 centimeter is got 10 millimeter. So 18 eta divided by gs minus 1 into rho w in gram per centimeter cube, g, or the rho, the density, because g is unitless, so we are not writing unit over here. Length we will be putting in centimeters, and time we will be recording in minutes. Okay, so because we are reading time in minutes, so I multiply this by 60, because over here we are recording it in seconds for the viscosity. So if you put these values over here and further solve this, the simplified form of this equation will turn up as this. Okay, so in this, the viscosity values you should be using in gram second per centimeter square, the density you will be using in gram per centimeter cube, the length you will be putting in centimeters, and the time you will be using the values in minutes. So always remember, when solving a numerical problems for the hydrometer analysis, you should know that you should be using these units. So if the value given is not in these units, then you will convert it. For example, the density is given in kg per cubic meter, so you will have to convert into gram per cubic centimeter or gram per cc, which is, by the way, 1 gram per cc. The unit weight of water is 1 gram per cc, constant at 25 degrees centigrade. So you can use this as 1 as well. So now, because on this hand side you can see all of these are constant at a given temperature and time. So because for any given water sample, the viscosity will be constant, the specific gravity of soil solids will be constant for that soil sample, and the unit weight of water is also constant as well. So we will replace all these constants over here. You can see all these constants, we will replace them with the value k. Okay, so over here you can see that k has been replaced, these are replaced with k, so k into L divided by T. This is what we have got, simplified form of this equation. So we need to determine the value of k, L and T to determine the particle diameter over here in millimeter at given time t. So now further moving on and determine the value of k, and then we will determine the value of L, and T is obviously the time which we will be reading on the recording on the stopwatch. So for the k value, you know, k is equal to 30 into eta divided by gs minus 1. Now k is a function of gs and viscosity over here, you can see. So if the specific gravity is changing or if the viscosity is changing, then the value of k will change. So following is the table which provide you all the values for different gs and viscosity values. You can use this table to determine the value of k, or otherwise if the viscosity of water is given to you and you know the specific gravity of soil solids, you can determine it using pycnometer method, so in the laboratory. So you can determine the value of k as well for your case. But over here in this table, they are already calculated for you because the water is universally available everywhere. So they have calibrated it and they have determined the value of k for different types and different specific gravity. So let's say your specific gravity of your solids is 2.6, okay, and the temperature at which you are doing the test, it's a hot day and the temperature is, let's say, 30 degrees. Okay, so you will come here 2.6 over here and 30 degrees temperature. So the value of k you will be using will be 0.0124. So you can just simply select the value of k from this table. Okay, no need to do some very fancy lengthy calculation. It will just directly give you the value of k in into minute per centimeter raised to power 1/2, which was the units we were using on the previous. So from this you can easily determine the value of k over here for any condition which you can have. For example, if you have got soil specific gravity to 2.6 and you are doing the test in winter and the temperature is 20 and the specific gravity is 2.65, so your k value will be equal to 0.0137 in this case. So very easy to determine the value of k over here in this equation. So k is done. This is how you determine k. Or if you have the soil viscosity provided in our laboratory, remember we have got viscometer. So you can, if you have water, you can just take it and you can determine the viscosity in the viscometer. This is available in your lab, and you want to determine specific gravity, then you can determine the specific gravity using the pacnometer as well. But remember, you have to determine the viscosity at the temperature at which you are be doing the test. So if you are going to do the test at 25 degrees centigrade, so you should make sure that you determine the viscosity at 25 degrees in the viscometer as well, and that will be the relevant viscosity which you can use. If the temperature is lowering, then the viscosity of the soil increases, viscosity of water, and if the temperature is increased, then viscosity of the water will reduce. So this is how you can determine the value of viscosity at GS if you don't want to use this table, or if you don't have this table. And examination, if you are given the viscosity or GS value, then obviously you have to determine the value of K. If the table is not given but these properties are given, then you will have to use this equation to determine the value of K. But remember, then you should remember the units, which is in gram and centimeters over here. So from this you can basically determine the value of K. Remember, we had rho W multiplied over here as well, but you know density of water is equal to 1 gram per cc, so it is multiplied as 1 over here, so that's why it is not being shown over here. If you remember on the previous slide, it was rho W over here as well. So rho W is also being replaced with K, but you can see the rho W is equal to 1 because viscosity of water is equal to 1 gram per cc at 25 degrees centigrade. So sorry, density of water. Now moving on for determination of value of L. So L, what is L? Because I told you that the hydrometer measures the specific gravity of anything at the center of the bulb. So L is basically the total immersion length of the center of this bulb from the top of the meniscus of the water. So this is the soil mixed with water in which you have placed hydrometer. Some of the particles have settled, some of the particles are still suspended form. So this length, which is usually represented as L over here, that will be the total immersion length, while this length will be known as hydrometer reading, or R, okay, or commonly known as L1 over here. So now what we have here is we've got this length L, we want to determine this. We have this L1, which is this reading which we can measure, because this is the 0 point and this is the point which you can visually see, and this is the length of the bulb. Now for this purpose, in case of our lab, we will be using ASTM standard 152H hydrometer, okay, so which has got the fixed volume of the bulb, and the length of the bulb is known in this case. So that's why you will be using this, because this will be helpful in determining the value of L. Now value of L is equal to L1 plus half of L2 minus VB divided by A. So I will not go into much detail of this. This is determined by the volume displaced by the hydrometer. When you place this hydrometer over here, it will displace, it will raise some water level over here, okay, so it will be and also it will raise some water level over here according to the volume occupied by this hydrometer. I should be drawing it over here in the bottom, but let's assume over here. Now once you can see over here, if we neglect the volume of this tube and only consider the volume of the bulb, because tube is very small, so we can neglect it, and the volume of the bulb. So half of the bulb is immersed over here, so only half of the volume is being raised by this portion above this height, okay. But over here, because full of the bulb is involved in raising this water level over here, so full of the bulb volume will be considered over here for raising the water level over here. So from this they have just worked out this and determined the value of L1, which you can read over here, and into half of L2 plus VB divided by A. Now L2 is constant for 152H hydrometer, which is 14 centimeter. Volume of the bulb is 67 centimeter cube, which is also cubic centimeter, which is also constant. for this 152H. Cross-sectional area of the sedimentation cylinder which we are using. The cylinder in which we are putting, this is also standardized, okay, and its cross-sectional area is equal to 27.8 centimeter square. So if you put the values into this equation, and also I want to determine the value of L1 as well. So these are the values on this, okay, these are the values you will put from here and this hand side, and I want to also determine the value of L1 as well, okay, L1. So for L1 we know that at 152H hydrometer, if L1 is 10.5 centimeter, then reading R is equal to 0, okay. So at this point the L1 from here to here, it is basically 10.5 centimeter. You can measure it using vernier caliper as well. So if the hydrometer reading is basically increasing towards down, okay, because it's 0 will be there and 60 will be here on the hydrometer. Once you pick it up in the laboratory, you can just check it. So, and if hydrometer reading is at 50 over here, then this reading R, if this is equal to 50, then this length will be equal to 2.3 centimeter. So from this we can basically work out the value of L1, okay, which will be over here 10.5 minus 2.3 divided by 50 and multiply by R, okay, which if you simplify this, then it will be 10.5 minus 2.3 divided by 50, which is 0.164 into R, and the values will be in centimeter. So for 152H hydrometer, you can use this equation to determine the value of L1. So L1 will be replaced with this value, and these values will be replacing with these. So if you put all these values into this equation, then L in this equation will be equal to L1, which is from here, plus these values are replaced 1 by 2. L2, as I mentioned, is 14 centimeter, okay, so it is replaced with 14, and then you have VB, which is volume of the bulb, okay, over here divided by the area. So volume of the bulb is 67 cubic centimeter, and the area of the sedimentation cylinder is equal to 27.8. So if you solve all this, you will get L is equal to 16.29 minus 0.164 R, and the value will be in centimeter, okay. So if you put hydrometer reading, these are the hydrometer readings. When you will be reading from hydrometer, this will give you the value R. For example, if the value over here is 40, then hydrometer reading R will be equal to 40. So you will just simply put 40 over here, and that will give you the value of L, and you will just put it in this equation. And time T will be the time at which you have taken this reading. Okay, you will have stopwatch, and you will be taking reading at 2 minutes, 4 minutes, 8 minutes, then 15 minutes, 30 minutes, 1 hour, 2 hours, 4 hours, 8 hours, and then the last reading you will be taking at 24 hours. So for one hydrometer analysis, you will be taking reading up to 24 hours. So at different times you will have different hydrometer readings. Okay, so you will prepare a table for you in which you will write time in minutes on the left, and then in the next column you will write hydrometer reading, and then also you will be recording temperature as well with that, which you will be using for temperature correction, etc. So this is how you will determine the value of L. So we have determined the value of K as well, and determined the value of L as well, and T will be obviously the time at which you have taken this value of L. So if you put the values into this equation, if you put the L value corrected for meniscus correction. Meniscus correction is what? When you place water, when you place hydrometer, you can see the water will be slightly concaving upward. So actual reading is basically here, and the reading which your eye will be seeing will be at over here. So you will be taking reading at this point and not at this point. So you will first do meniscus correction over here for this and then use the value of L. So R value will be taken for meniscus corrected and then you will put in over here. So they have, for standard ASTM 152H, they have given you the value, various value of hydrometer reading. They have placed the hydrometer reading in this equation R and they have given you the value of L. For example, if I put R is equal to 0, then L will be equal to 16.29. So you can see over here R is equal to 0, it is 16.29, which is rounded to 16.3 over here. So similarly, you can put the value of R is equal to 1, R is equal to 2, R is equal to 3, etc. in this equation, and you can determine the various values of L. So from this table also you can determine value of L. If you know the hydrometer reading R, let's say hydrometer reading R is equal to 20, then L is equal to 13 in this case. So you will just place value of L is equal to 13 into this equation. Okay. Also you will get the value of K for temperature and GS. You know, I showed you the table for the K value for the various temperatures and various GS, specific gravity values. So get the value of K from that table and put in this equation, and T will be the time at which you are recording this. Okay, whether it is like 2 minutes, 4 minutes, 8 minutes, 16 minutes, 1 hour. So if it is 1 hour, then you will write T is equal to 60 minutes. If it is 2 hours, then you will write T is equal to 120 minutes. If it is 4 hours, then you will write T is equal to 240 minutes in this equation. So you will put these values and you will get the value of the diameter of the particle sizes which have settled during this time. So from this you can plot the combined gradation curve. Remember, I told you that the particle sizes greater than 75 microns, they are plotted using the sieve analysis. So this portion is for sieve analysis, shown with the circle. Okay, so these are the particle sizes measured using sieve analysis, and these are the particle sizes which are shown by these triangles are measured with the hydrometer analysis over here. Okay, so if we plot them on one graph, because we want to see that how much are sand in a given soil and how much is silt in clay, because silt in clay is finer than 75 micron, so we can not determine their sizes using sieves. So we will determine them using hydrometer, and the larger particle size, the core sizes, we will determine them using the sieves, and then we will plot them on the same graph. So it will tell us that how much percentage a particular soil size is there. For example, I want to know how much percent is 0.02 millimeter soil. So 0.02 from here, and I will come on this graph over here. So it's approximately, like you can say 35%. Okay, so 35%. Similarly, I want to see how much is 80% size in this. So 80, from 80% I will come here and I will then drop this line downward, and you can see over here between 0.2 and 0.1, like 0.15 maybe. So 80% of the particles are 0.15 and smaller, 0.15 millimeter and smaller. Okay, so 0.15, you can see there are smaller sizes than this. Okay, less than 80. So as you can see, 20% of the particles are greater than 0.15 millimeters. So this is the one of the use of this combined gradation curve, from which you can see that how much percent a particular size is present, or how much percent of the soil is less than the particular size. Okay, so if I want to determine that how much particles are less than 1 millimeter in this, so I will just go from 1 millimeter and see over here. So I can see over here more than 90% of the soil is less than 1 millimeter. You can see, because more than that is 90% line, and all of the soil over here, all of these sizes are below this 90%. These are the soil sizes which are above 90%. So from this you can determine the various particle sizes, and you can play around with that. You can determine that if soil is a coarse soil, if it is fine soil, or how much percent is the coarse soil in this, how much percent is the fine soil in this. Also remember, then when you plot the combined gradation graph, you will see there will be some small kink over here, and they will not actually start from the same point, but you will see the combined gradation, the graph will show you that the particle sizes coming from hydrometer analysis, they will be slightly towards the right of the graph in this case. This is discontinuity is because of the irregular shape of the soil particles, because we have considered the soil particle to be sphere, while in reality the soil particles are basically flaky in shape and sometimes like needles in shape. But for the sake of application of Stokes law, and Stokes law is applicable to only spherical particles, so because of this we have got this inconsistency. So there are some limitations to Stokes law over here, which can give you the result accurate up to some limit, but still it is useful over here to be used to determine the soil particle sizes. So hopefully you have enjoyed the lecture for today. In next class we will discuss the properties of this particle size distribution curve or S curve or your gradation curve, and determine the various parameters which can easily tell you if your soil is a particular type of soil is useful for a particular purpose, if it is uniformly graded, poorly graded, well graded, etc. So all these things will be discussed inshallah in the next class. So see you soon. Take care. Thank you very much for listening.